Okay. Chapter 10, Jordan Canonical Form. Yeah. In this chapter, we will learn section 10.1 and 10.3, finding the Jordan canonical form with a dot diagram, and the usage of computer algebra system to do those computations, to draw the dot diagram. Section 10.1, finding the Jordan canonical form with the dot diagram. If a given matrix is diagonalizable, then everything's easy. All you have to do is do the computation on the diagonal matrix. Then to draw your conclusion. So it's easy. But not every matrix is diagonalizable. So in this section, we will introduce a method for finding a Jordan canonical form of a non-diagonalizable matrix by using similarity transformations. For example, this matrix 2 by 2 matrix 1, 1, 0, 1, and this 3 by 3 matrix are non-diagonalizable. We can easily verify. If suppose there is a non-singular matrix S that makes S inverse AS is equal to a diagonal matrix, then it occurs a contradiction on these two examples. Okay? Here. For every square matrix A, one can obtain a block diagonal matrix called the Jordan canonical form matrix that is similar to A. That's the key. Even though a matrix is not diagonalizable, we can find a similar matrix, similar block diagonal matrix from any given matrix A. Here is the review of what we have learned. Let A be an n by n matrix. Then A is diagonalizable if and only if it has n linearly independent eigenvectors. Okay? Okay. And normal matrix is unitarily diagonalizable. Normal matrix is a matrix that satisfies A conjugate transpose is equal to A conjugate transpose times A. A normal matrix is unitarily is always unitarily diagonalizable. But not all diagonalizable matrices are normal. Okay. If a matrix A is diagonalizable, then each eigenvalues of A generate an eigenspace with a dimension equal to the algebraic multiplicity of that eigenvalues. Okay. Each eigenvalue has the eigenspace with dimension equal to the algebraic multiplicity, then which means if we add up all those algebraic multiplicity, then it will be the size of the matrix, which means we have the number of linear, n number of linear independent eigenvectors, which means A is diagonalizable. That's what it says. Okay, these are review. Theorem 10.1.1. Let A be an n by n matrix with T linearly independent eigenvectors. Then A is similar to a matrix of this form, where if you have a T linearly independent eigenvectors, then we have a T. This is a block diagonal matrix, J. Which is unitarily similar. This comes from Schur's theorem. From Schur's theorem, we can go further and further to reach this point for some unitary matrix. Furthermore, we have this JK, this block, these diagonal blocks, has the form like this. The main diagonal entries are eigenvalues, and the super diagonals are 1, but all others are 0. Okay? Here we only have eigenvalue lambda I and 1 and zeros. If we add up the size of this block matrices, then it should be n by n. So it should be n. Okay. We call this is a Jordan block, like I told you. This is a Jordan block, and this block diagonal matrix JA is called Jordan canonical form of given matrix A. So JA is a Jordan canonical form of A, and this JK is a Jordan block of the matrix A and JA. This Jordan canonical form of matrix A is a block diagonal matrix composed of Jordan blocks. So this Jordan canonical form is a block diagonal matrix each of the diagonal blocks are Jordan blocks. Property of Jordan block. Lambda, for a given eigenvalue lambda I of an n by n matrix A, its geometric multiplicity is the number of linear independent eigenvectors associated with lambda I. That's okay. If we have a if lambda I has 3 linear independent eigenvectors, that means A has 3 Jordan blocks corresponding to this eigenvalue lambda I. Okay. Suppose lambda 2 has a 2 linearly independent eigenvector, that means it has 2 Jordan blocks corresponding to lambda 2. That's okay. The sum of the size of all Jordan blocks corresponding to eigenvalue lambda I is the algebraic multiplicity. Okay. So if we have a eigenvalue whose algebraic multiplicity is 10, then addition of the size of Jordan block corresponding that eigenvalue, it should be same as the algebraic multiplicity of that particular eigenvalue. If the geometric multiplicity and algebraic multiplicity of every eigenvalues of A are equal, that means what? Sum of the geometric multiplicity of all the eigenvalues is equal to n, which means you have n linearly independent eigenvectors, which means A is diagonalizable. Okay? So every size of Jordan block is 1 by 1. That means you have n Jordan blocks, which is 1 by 1 Jordan blocks, which means the Jordan canonical form is a diagonal matrix. Okay? For the diagonalizable matrix, simply we say it is a simple matrix. Okay? If a matrix is diagonalizable, we call it a simple matrix. Okay. Consider this Jordan canonical form of a matrix, JA. This has how many Jordan blocks? This has 4 Jordan blocks. Okay? Okay. And how many? What's the characteristic polynomial of this matrix? The characteristic polynomials are the main diagonal entries of this upper triangular matrix here. So we have 4 number of eigenvalue 2, and we have 2 number of eigenvalue 3, and we have 2 number of 0 eigenvalues. Okay, so characteristic polynomial should be like this. So the matrix, this Jordan canonical form, and the matrix has this characteristic polynomial, and this Jordan canonical form it has the 4 Jordan blocks, okay, consisting of 3 by 3 and 1 by 1 and 2 by 2 and 2 by 2. Okay. So A is a 8 by 8 square matrix whose characteristic polynomial is like this. Yeah. So we can tell something on matrix A from the given Jordan canonical form. Here, how the algebraic multiplicity of each eigenvalues determine the number of times that eigenvalue appears along the principal diagonal of Jordan canonical form of A. Okay. Notice it. For example, 2 appears 4 times, and while 3 and 0 appears 2 times. Hence, the algebraic multiplicity of 2 is 4. Yeah, we have 2 appears 4 times. Algebraic multiplicity of 2 is 4. Algebraic multiplicity of 3 is 2, and algebraic multiplicity of eigenvalue 0 is 2. Okay, that's what it says. You can easily verify the sum of the size of all Jordan blocks corresponding to a single eigenvalue is also equal to the algebraic multiplicity. Okay. So if you add up the size of Jordan blocks, then that's same as the algebraic multiplicity of eigenvalues here. And here we have a 2 by Jordan block 2 by 2 for 3, then this the algebraic multiplicity. And the size, the addition of Jordan block, the size of the Jordan block for corresponding eigenvalues is same as the algebraic multiplicity of eigenvalues. Those are the properties. Okay. And what's the geometric multiplicity is of eigenvalue is the number of number of Jordan blocks. So what's the number of Jordan blocks of eigenvalue 2? 2. So that's the geometric multiplicity of eigenvalue 2. We have one Jordan block for eigenvalue 3, which means geometric multiplicity of eigenvalue 3 is 1. And we have one Jordan block corresponding to eigenvalue 0, which means geometric multiplicity of eigenvalue 0 is 1. Okay? So it has those informations. Think about the 5 by 5 matrix. This Jordan block. This is 5 by 5. So think about the 5 by 5 square matrix A, if A has only one eigenvalue lambda with one associated linear independent eigenvector, then what? Its Jordan canonical form of A is since it has only one linear independent eigenvector, so Jordan block is we have only one Jordan block. So we have a 5 by 5 Jordan block here, and all the eigenvalues are lambda, and since it's one Jordan block, we have the ones on the super diagonal entries, and all others are 0. Okay. So we have one Jordan block of eigenvalue lambda, 5 by 5 Jordan block. Here. So this information tells us the Jordan canonical form of it. Because the number of linear independent eigenvectors of A determine the number of Jordan blocks in the Jordan form of A. Thus, in this case, the geometric multiplicity of the eigenvalue is 1, because we have only one Jordan block and one linear independent eigenvector, which means the geometric multiplicity is 1. But algebraic multiplicity is a number of eigenvalues. We have 5 eigenvalues of same lambda. Okay, so the algebraic multiplicity is 5. So these are the relationships that we can find between the matrix and the Jordan canonical form of that matrix. The next question is how to find the Jordan canonical form. How to find it? How to find it? Okay. Suppose we have a matrix A, n by n matrix, and k distinct eigenvalues, lambda 1 to lambda k. Then we have what? We have a block diagonal matrix like this. K block diagonal. K block matrices like this. But for each lambda I, each lambda I may have the number of Jordan blocks in it, like this. Okay. Okay. So our goal is to figure out what's the size number of this Jordan block for each lambda I, and what's the number of the Jordan blocks for each lambda i's. If we figure out all of these for each lambda I, then we can have all Jordan blocks that we need to find the Jordan canonical form of A. Okay? So that's the idea. Then how we can find? As I mentioned, we will consider, we will use the information on rank of A minus lambda I, because A and Jordan canonical form of A is similar. So rank of A is same as rank of JA, and also rank of A minus lambda I is same as rank of JA minus lambda I. So we will use these informations. And you have read this, so I will start to introduce the idea of dot diagram property. Dot diagram consists of L columns. That's the number of Jordan blocks, okay, and columns. And counting from the left to right, the j's column consists of the kj dots that correspond to the eigenvectors of xj, and starting with the initial vector at the top and continuing down to the end vectors like this. Okay, this is the idea of dot diagram. Okay, compute is, if you have a matrix A, then you can compute A minus lambda I for each lambda. Okay, for each distinct lambda, and you can find the rank of A minus lambda I, and also you can find the rank of the square of A minus lambda I, and cube of A minus lambda I, and so on, like this. Okay. And so since you can find those powers, so you will be able to to form this diagram. Actually, what this says is, if you the L is the number of the linear independent eigenvectors. So suppose you have L linear independent eigenvectors like this, then we can compute the corresponding eigenvectors and next, and so you can find the generalized eigenvector on this sequence from x1, and you can find the generalized eigenvector from this sequence, and you can find the generalized eigenvector of this sequence to find the matrix Q that makes Q inverse AQ is equal to Jordan canonical form of A for eigenvalue lambda. So this is the whole idea of the dot diagram. Okay. Here, Xi's are linear independent eigenvectors associated with the lambda I. So here we should have lambda I is there, and here this gives us the information of the how many Jordan blocks do we have, and what's the size of Jordan blocks for the corresponding eigenvalue lambda I. 여기다가 lambda i를 써줘야 되는 게 맞다. Okay. Anyway, okay, lambda. So here, let Rj denote the number of dots in the jth row of the dot diagram. Then R1 is the number of Jordan block of size at least 1 by 1. And if then R2 is the number of Jordan blocks of size at least 2 by 2. And Rp1 is the number of Jordan blocks of size at least P1 by P1. So, yeah, the Ri's is in decreasing order. The sizes are decreasing. Yeah. And the following example shows what we discussed in the textbook. For example, for 9 by 9 matrix AI, suppose we have an AI matrix whose main diagonal entries are lambda I, eigenvalue lambda I. The number of Jordan blocks are L in it, and the size of Jordan blocks is completely determined with those PIs that we saw in here. PIs. Here, let's see. To see this, here, L is 4. In this case, we have 4 Jordan blocks, so L is equal to 4. And the first block is 3 by 3 block, so P1 is equal to 3. And second block is 3, so P2 is 3. And so third block is 2, so 2 by 2 block. And fourth Jordan block is 1 by 1, so P4 is equal to 1. So if we know this L and the PIs, then we can find this Jordan canonical form. And if we have this, then we can find this L and PIs from here. So with this, the Jordan block is uniquely determined if we order those Jordan blocks in the decreasing size like this. To find the dot diagram of AI, here, in this case, L is equal to 4, and P1 is equal to 3, and P2 is equal to 3, and P3 is equal to 2, and P4 is equal to 1. So dot diagram of this Jordan canonical form can be drawn in this way. We have 4, the first row is 4, and the first L is the first row. That's the number of Jordan blocks. And no. First, 1, 2, 3, 4. We have 4 columns, so we have 4 points. So we have 4 columns, so L is equal to 4. And first column, we have point 3. Second column, P3, P2 is 3. P2 is 3. P3 is 2. We have 2 points, 2 dots here. P4 is equal to 1 like this. So actually, this Jordan canonical form has its corresponding dot diagram like this. From this dot diagram, we can draw this. It has 4 Jordan blocks. The first one is 3 by 3, second one is 3 by 3, third one is 2 by 2, fourth one is 1 by 1, like this. So from this, if we can find the dot diagram, then we can draw the Jordan canonical form that for the corresponding eigenvalue lambda I. That's the idea. And this comes from this theorem 10.1.2. If the number of dots in the first R rows of dot diagram for lambda I is equal to the dimension of solution space of this equation, the R's power of A minus lambda I density matrix times X is equal to 0. That's actually same as the nullity of this matrix. This is a theorem. Yes, here. This is the whole idea. That comes from the observation that we made on the blackboard there. The null space of this, which is same as null space of JA minus lambda I times identity matrix to the R's power. The same, similar, because A and Jordan canonical are similar. So from that observation, so we can, if we know this, then that's exactly gives us the number of dots in the first R rows of dot diagram for lambda i's. This is the observation. By using the observation that we had on the board. Okay, here is the theorem 10.1.3 that gives us Ri's. For the matrix A, let Rj denote the number of dots in the jth row of the dot diagram of lambda I, then the followings are true. First, R1 is equal to n minus length of A minus lambda I. Okay, that's the number of Jordan blocks. Okay. Next, if J is bigger than 1, then Rj is equal to length is equal to the difference between length of this minus length of this. That gives us Rj. Okay. The length, if we do one more power, the length will be decreased, as you see the observation of the length of J minus lambda I times identity matrix to the case power. Here's the proof. As we know, the addition of this R1 through the Rj is equal to the nullity of the J's power of A minus lambda I times identity matrix, which is same as n minus length of this from the length nullity theorem. Okay, here. And R1 is equal to the n minus length of A minus lambda I times identity matrix. And Rj is what? So addition from this Rj can be written as this minus this, because all will be cancelled and only Rj left. So this can be written as this, because this is just part of the first part of this. So this can be written in this way, which is the same as, this can be written from here. This can be written as n minus length of this minus n minus length of this. Okay? Which is 그래서 여기서 좀 오타가 있는 것 같다. Okay? Yeah, I see. Yeah, that's right. This is correct. Yeah, this can be written as this can be written as this, and n's are cancelled, and minus makes this come to here as plus sign, and minus length of j's power comes here. This gives the second part of it. So the number of dots in each node, rj, here means the number of blocks of size n least j times j. Okay, so the observation, from the observation and the computations, yeah, we found the relationship between Ri's in this way. Okay, with those, yeah, we can now we can find the Jordan canonical form of any given matrix. Suppose if we have a matrix A like this, then we can find the characteristic polynomial of the matrix A, which is this, which means we have eigenvalue 3 with algebraic multiplicity 1, and eigenvalue 2 with algebraic multiplicity 3 here. So the characteristic polynomial is this, and it has two distinct eigenvalues. For lambda 1, which has algebraic multiplicity 1, so we only have just one dot, because the algebraic multiplicity is only 1. We don't have to compute anything. For eigenvalue lambda 2, which is 2, then we can find the length of a minus 2I, and we can then the length of the square of a minus 2I, which is 2 and 1. So R1 is 4 minus length of a minus 2, 1, which is this, which gives us 4 minus 2 is equal to 2. So R1 is 2, okay? And R2 is the difference between these two, which is 1, which means the R1. First row, we have 2 dots, and first column, we have 2 dots, and R2 gives 1 dot in the second column. So this is a dot diagram for eigenvalue lambda is equal to 2, okay? Which, so what we have is, we have what? We have 2 Jordan blocks here. We have 2 Jordan blocks. One is 1 by 1, and one is 2 by 1, and one is 1 by 1 for eigenvalue lambda 2 here. We have a 2 by 2 Jordan block and 1 by 1 Jordan block for the eigenvalue lambda 2. So for lambda 1, we have only 1 dot, so which says we have 1 Jordan block of 3, and we have 2 Jordan block for eigenvalue 2, like this. So A1 is 1 by 1 Jordan block, and A2 is a block diagonal matrix which has 2 Jordan block corresponding lambda is equal to 2, like this. So Jordan canonical form A is like this. And this also can be found with this. So we define a matrix A, then this command, finding the Jordan canonical form of A, gives us this, which is the same as what we found here. 1 by 1 Jordan block for eigenvalue lambda 1, and we have 2 Jordan block corresponding to eigenvalue lambda 2, and that has 2 Jordan block. One is 2 by 2, and one is 1 by 1, like this. So we can do the same thing. Find the Jordan canonical form of A, of this 4 by 4 matrix. Then we can find the characteristic polynomial, which we have 2 distinct eigenvalues. And so think about the dot diagram for lambda 1, and think about the dot diagram for the lambda 2. Let's say lambda 1 is 4 and lambda 2 is 2. For lambda 1 is equal to 4, we can find R1 by using the formula 4 minus length of A minus lambda 1, that you can easily find it. Since you do have a tool So you can compute A minus, you can find eigenvalues. If you have a matrix, then you can find eigenvalues. Then you can find the A minus lambda I. You can find the rank of it. And so you can find the R1 from the size of the matrix minus the rank of A minus 4I, which is 3 here. So R1 is 1, okay? Which means we have the one Jordan block of size at least 1 by 1. Okay? But so we have one Jordan block. That means we have 2 points. So this for lambda 1 is equal to 4. The algebraic multiplicity is 2. So that means we have 2 dots. But we have R1 is equal to 1. So which means we have only 1 dot on the first column. So the left 1 dot should be on the should go to the second row, and first row and second row. So which means we have 2 dots in the first column, which means we have 2 by 2 Jordan block for the lambda 1. Next, lambda 2, we can find lambda 2 equal 2, we can find the R1, which is 2, which means we have 2 dots on the first row, which means we have 2 number of Jordan blocks, which means we have 1 by 1 Jordan block for the eigenvalue lambda 2. Okay, so we have 2 Jordan block like this. So we have A1 like this and A2 like that. So the direct sum of these two will give us a Jordan canonical form of that matrix. Like that. Okay, so all these things is if we can compute these, and then we can easily draw the dot diagram. Then from there we can draw the Jordan canonical form. So this can be coded with this command. So for a given matrix, if we check our solutions, then we will have this, which is same as to what we found. Okay, that's the end of section 10.1, and here is the information of the more information on Jordan canonical forms. Here we do have a Jordan canonical form definitions, and here is the information for the generalized eigenvectors. And here it gives us how to find the Jordan canonical form after we find the generalized eigenvectors. See, if you have a generalized eigenvectors, then we can form a matrix Q that makes Q inverse AQ is equal to Jordan canonical form. So we can find it. In the other way, if we find the Jordan canonical form first, then we can easily find the corresponding generalized eigenvector of the suitable size to form n linear independent column vectors of the matrix Q that makes Q inverse AQ is equal to Jordan canonical form. Those columns form generalized eigenvectors. So if we can find either one of them, then we can do everything. And it has applications on characteristic polynomials and minimal polynomials, and Cayley-Hamilton also can be treated with this Jordan canonical form, and the applications contains to compute the J's case power. For example, here, if we have a Jordan canonical form like this, and the blocks, then the power of the Jordan canonical form can be obtained much easier way. Okay, so if we do make a power of Jordan canonical form like this, then it also we can have it without any difficulties. And also, with it, the case power of matrix A can be computed with the help of Jordan canonical form, because A's case power is same as this. So if we can find the case power of Jordan canonical form of A, then the finding A to the case power is much easier. We can save a lots of time and money to do compute this case power. Okay. For example, yeah, if we do, okay, here we have to start from define a matrix. We have to define a matrix A, then we have a J matrix and Q matrix. So Q inverse AQ is a Jordan canonical form like this. Then from there, find the Q inverse. So we can check, yeah, the Q times Jordan canonical form times Q inverse is the case power of Jordan canonical form, and then multiply Q and Q inverse is same as just fifth the case power of the A matrix. So as you see, they are same. Okay? But as you know, if the matrix size is bigger, then this using Jordan canonical form is much efficient way to do it. And the same thing, the powers and those things. For any arbitrary power, then we can find it in the form like this. And also, yeah, Jordan canonical form can be used in the many way to find the Q's and things. So anyway, yeah, you can take a look on those, and also by using this Jordan canonical form, you can find the matrix function. With it, you can compute the matrix functions like e to the A, like this. Exponential function can be treated in this way. So e to the matrix A can be defined by using the Jordan canonical form like this. Okay? If you find the Jordan canonical form, then e to the matrix A can be defined in this way. Okay? And e to the A can be found in this way. And also, using those Jordan canonical form, yeah, we can find we can solve the linear system of differential equations. The Jordan canonical form can be used for these ordinary differential equations. So it has a lot of applications that is essential to do the matrices. I think that's the end of section 10.1. And now, yeah, I will show how do we compute the Jordan canonical form in section 10.3. Any questions?